All right, ladies and gentlemen, we are going to go through the notes on the modern atomic theory. We left off on atomic theory with Bohr, and what I want to do now is explain the experiments and what we found through the experiments that allowed Bohr to experimentally argue that electrons were arranged around the nucleus in layers called energy levels. And at the end, we'll talk about why and how this informs the design of the periodic table. So the classic atomic theory was where we left off with Rutherford, that matter is composed of atoms that contain known numbers of protons, neutrons, and electrons, that atoms of each element have unique properties that set them apart from other elements, meaning hydrogen atoms are different than helium, helium's different than lithium, and so on. Atoms of each element have unique properties. Atoms of the same element have the same number of protons. That's the identifier. What makes an atom a particular element is the number of protons, the atomic number. Protons and neutrons are found in the nucleus, and electrons are found in this cloud outside the nucleus. Where we left off with Rutherford, he had the nucleus with protons and neutrons, and somewhere out here is where the electrons were. What we want to look at then is what caused us to look beyond Rutherford's model. So the catalyst for a new theory was that Rutherford's model was insufficient in that it could not explain where the electrons were, or it could not explain why atoms that differed only by one proton would display such wildly different characteristics, meaning something like helium or neon that are a element, a proton away from things like lithium and sodium. Helium and neon are completely unreactive, but lithium and sodium are extremely reactive. What makes that swing so fast? So during the early 1900s, some chemists, particularly physicists, conducted several experiments that showed Rutherford's nuclear model of the atom was incomplete, and we want to look at the experiments and what we learned from them. First and foremost was the photoelectric effect. Some scientists observed that electrons can be knocked off of the surface of a metal if a light with a specific wavelength or frequency is shown on it. So the photoelectric effect is the effect that when you shine a light with a certain frequency onto a metal, it can actually cause electrons to get knocked off of the surface and flow across a tube from one electrode to the next. It can actually create current and eventually light. The result was that we needed to acknowledge that light that we thought of only as a wave before could actually be treated or studied as a particle. Because of an electron is a particle, the only way to dislodge it from the surface of the metal would be if the light that was shining on it was acting like a particle. And we call these light particles photons. If we look at this really quickly as a simulation, what we'll see here is that the light frequency can be adjusted here. And if we have sodium over here, this is sodium metal, and we start to work our way through the spectrum from red into orange into yellow and then green, we're going to start to see electrons being knocked off the surface, moving across from the negative to the positive electrodes. And that shows us that light here is acting as a particle and knocking electrons off of the surface. Each metal has a very specific frequency of light that this begins at. But the main thing that it showed us above all else is that things that we consider to be waves can also act as particles. There's a dual nature. Well, Bohr kind of took that idea and flipped it on its head. And when he was studying elements, he took them and he heated them up. So he took things like hydrogen gas and he put them in a tube and passed super high voltage electricity through them, kind of like the light bulbs that we have above our heads at school, the fluorescent light bulbs. That's just a glass tube that has some gases in it that when you allow electricity to shoot one side to the other, it actually gives off a certain color of light. These images down here are showing a electrode being heated to the point of incandescence. All that means is that it's being heated up until it glows. So you take something, a metal, and you make it white hot, and it ends up giving off a certain color of light depending on the element that you're heating up. So Bohr said, if we can study light as a particle, why can't we study the particles, the electrons, in an atom by the light that they give off? And what he came across was looking through these with a prism. Every element had a very distinct set of lines of light that were given off. Everything else was kind of blank, but there were very discrete, distinct lines of light that were given off by an element when it was heated to the point of incandescence. Okay? So you can see hydrogen has very few lines. It has 4 lines in the visible light spectrum, and we'll talk about where that falls in a moment. But when we look at mercury, you have 1, this is actually a double line, 2, 3, 4, 5, 6, 7, 8 lines of light that are able to be observed if we look at the light from a mercury lamp going through a prism. So these are called emission spectra. They weren't continuous, meaning there were very distinct lines of light. And then with some help from some guys named Planck and Einstein, I'm sure you've heard of Einstein, Niels Bohr proposed that the spectrum that we were seeing, those lines of light, were showing changes in the energy for electrons in the cloud. They were jumping, and since it wasn't continuous, there were only certain specific jumps that they could make within the electron cloud. Max Planck called these quanta, and he went through a whole bunch of calculations to figure out that they were all a whole number ratio of this value. Okay? Mainly what he was able to figure out is that each line of light had a very distinct energy that you could calculate from his constant and the frequency of the light, or his constant, the speed of light divided by frequency, or by wavelength, I'm sorry. Energy is Planck's constant times the speed of light divided by wavelength. You can see those variables are listed down here below. After Bohr examined Planck and Einstein's discoveries, what he proposed is that the electrons were actually jumping from energy level to energy level, that there were very distinct layers in the electron cloud. If the energy is lost when the electrons jump back and forth between the energy levels. So if we skip down here to the bottom for 1 second, here's your nucleus, and then you can see there's one layer of electrons here, there's another layer of electrons on this atom out here. These electrons, if they absorb energy, can jump out to here, but then they need to drop back down at some point. So when they drop back down, that gives off energy as light. So where they normally exist in their non-excited state is called the ground state. When they jump out because they absorbed energy, that's called the excited state. So they exist in the ground state, they absorb energy and jump out. When they come back down to the ground state from the excited state, so ground, jump to excited, back down to ground, they give off light, and that's how we can tell how far that they've jumped. Now, the way that we study this is we use electromagnetic radiation, which very simply is any form of radiant energy that exists as a wave in the universe. It can exist with or without matter present. So they can exist in air, but they can also exist in the void of space. And what I want you to notice on this diagram is that as the wavelength is getting smaller, the frequency is actually going up. So you can see the waves are getting tighter and tighter together. Frequency is increasing. If we put another layer here of energy, we would say that energy goes up as wavelength goes down, or energy goes up as frequency goes up. And the visible light spectrum is this very, very narrow band of electromagnetic radiation in the middle of all these different waves, from radio to microwave, all the way through X-ray and our gamma rays from our nuclear decay. Now, the light given off by samples was EMR, so we got to remember that. We have to remember that all EMR travels at the speed of light, and that what we really need to understand conceptually is that energy increases when frequencies are higher and wavelengths are shorter. Energy decreases when we have lower frequencies and longer wavelengths. This means that as we observe the visible light that elements give off, the amount of energy released increases as you work through the spectrum. So if you observe something that gives off red light, it's giving off lower energy light than something that gives off violet or ultraviolet light. So if we reflect back on the emission spectra that we observed above, that means that each of the lines observed in those spectra represent different jumps. So each color represents a different degree of jumping or falling back down from the excited to the ground state. So each line represents a distinct jump. And then Bohr's model then allows us to explain most of the properties of the atoms based on two factors: the number of electrons in the outermost energy level and the number of energy levels in the atom's electron cloud. In our next lesson, we'll explore that a little bit more in our next set of notes, and we'll take some time to really look at how the table informs us about the number of energy levels that an element has, and it also tells us how many electrons are on that outermost level that determine reactivity. So we'll pick up there. Please feel free to go back and review, and then you have your assignment will be listed in the module next down below this video.